Hello class, this is Mr. Lehman. I want to talk to you today about double replacement reactions and how we can predict the products of them, and then how can we show what's happening in that reaction by writing ionic equations. Alright, so remember, single and double replacement reactions have to occur in solution. That means that they have to be aqueous, they have to be dissolved. And so let's think about why that is. So I have a picture of the crystal lattice. Ionic compounds are made up of positively and negatively charged ions. And so a crystal lattice here, we have our positive sodiums, the little purple balls here, surrounded by negative chloride ions. And for every one sodium, there's one chloride ion. And so there's a 1-to-1 ratio between all these ions. And so we get the chemical formula NaCl. Remember, formulas have to be neutral. So the positive 1 sodium, the negative 1 chloride add up to 0. And that shows how we have a balanced chemical formula. Our chemical formula adds up to 0, the rule of 0 charge. So ionic compounds are held together. These particles, these ions are held together very, very tightly, very, very strong ionic bonds. So the only way that we can have a replacement reaction occur is we need to be able to have these ions switch places. And the only way they can switch places is if they're dissolved in water. So if we take this crystal lattice and we put it in a beaker of water, it's going to dissolve. And so I mean dissolve, it's going to split up into the ions that it's made up of. So the Na positive 1 ions and the Cl minus 1 ions are going to separate because they're attracted to polar water. Remember, water has oppositely charged ends, the positive end, the hydrogen end, and a partially negative end, the oxygen end. And so the water is going to do a good job of attracting to the ions and separating it. And so the sodium and the chlorines are no longer going to be floating around together, but they'll be floating around separately in that beaker of water. And that allows them to switch places and to react with other things. So solid sodium does not react. Sodium chloride that is dissolved in water, aqueous, can react. That's what we want to talk about. Will it react? How do we know if it's going to react? And things like that. So what you're looking out for is a double replacement reaction has to be one of 3 criteria. It either has to produce a precipitate, it has to produce something molecular like water that's going to stick together, or a gaseous product that will leave the beaker and go off on its own. So we need to produce something that's going to separate itself from the solution and not stay dissolved as ions. So here we're mixing 2 chemicals. We're mixing solution A, aqueous substance A, with aqueous substance B. And when this reaction occurs, we make a precipitate here. So this yellow cloudiness, that's a solid. That's our precipitate. And the majority of the reactions that we look at this unit will make this precipitate, which is a solid that's suspended in a water. That'll separate, will settle to the bottom over time. So how do we know if a precipitate is going to form? Well, let's look at an example reaction. So in this reaction, we have aqueous sodium sulfate. So remember, sodium is +1, and sulfate ion is a polyatomic ion, it's -2. And that's why we need 2 sodium ions to cancel out the 1 sulfate ion because of the difference in charges. Lead in this instance, lead is going to be a +2 ion here. And when it combines with nitrate, nitrate's -1. So once again, we need 2 nitrates, and because we need 2 of this group of atoms, we have to put parentheses around it. Only when you have multiples of a group of polyatomic ions do you need parentheses. Notice I didn't put parentheses around Na because we don't need parentheses there. Alright, so when these 2 things react, in theory what can happen here is the sodium ions, the positive sodiums, and the positive lead ions, or 2 metal ions, can switch places. So if lead comes over here and links up with the sulfate, so Pb has a +2 charge and sulfate has a -2 charge. And so that's the correct chemical formula. It adds up to 0. We got to look at our solubility chart and see, does it dissolve or does it not dissolve? And where it intersects on my solubility chart that I'm looking at right now, it says S, solid. And that means precipitate. So this down arrow means it's going to be a solid, a precipitate that's going to form. Just like we saw here, this yellow cloudiness, that's a precipitate. We showed that's a special solid produced in this reaction called a precipitate by putting a down arrow. And then over here we have the sodium +1 sodium linking up with the -1 iodide. And I look at my solubility chart, and group 1 metals are always aqueous. They always dissolve. They love water. They're attracted to water. Alright, so there is our reaction equation. Notice it's not balanced. I have 2 sodium ions and 2 nitrate ions on the left side. So I would need to show that there's a a 1 to 1 to 1 to 2 ratio between these reactants and products. Alright, so that is how we predict if a double replacement reaction will occur. So the positive ions are going to switch places. Then I got to look for, did I make a precipitate? Yes. If I did make a precipitate, if I made two aqueous substances, then I have to look for, did I produce water or did I produce something that's a gas? If I produce two aqueous things, then the reaction will not take place because everything's still dissolved in the water and nothing has changed. So now let's write the ionic equation for this. And I'm going to start a new tutorial for that.